Hi everyone, this is going to be the final third of the chapter 12 lectures. And so we've spent the first two lectures about naming and studying the structure of alcohols, thiols, aldehydes, and ketones. So what we're going to look at now is just a select few types of reactions that these molecules can undergo. And predominantly what we'll be looking at is oxidation reduction reactions. And so before we even jump into that, I'll just remind you really quick, right? So I usually use Leo the Lion Goes Grr to remind myself what is being oxidized and what's being reduced. So I say Leo, Grr. Another common one is oil rig, right? The idea, so for me, you can use whichever one you want. I'm just going to go with my old high school fallback. I mean, it's been a zillion years, but it still works. Right, the way I look at it is loss of electrons. Let me do that in a different color. We'll do loss of electrons is oxidation. And gain of electrons is reduction. Something to add to this, and we didn't cover this before, but this is kind of the old school definition. I know I've mentioned it, but we never really focused on it too much. Sorry if you can't really see that, but it says addition of oxygen. Reduction is sometimes the addition of hydrogen. And so we'll see that this example, this other alternative definition, which is a little less specific, but is actually going to help us a lot more tracking what's happening with these reactions. So don't lose your original definition about tracking where electrons go. Oxidation reduction reactions can also happen by shifting electron density. So you don't necessarily need to transfer an electron. You can just shift density. And then so this addition of oxygen being oxidation, or addition of hydrogen being reduction, is going to help us track that a little bit better with ionic compounds. With molecular compounds that aren't necessarily fully charged like ionic compounds. So let's start with alcohols. So this will be our first real type of reaction that's not oxidation reduction. The rest will be pretty much redox reactions. So the reason why I chose to start with this is because it's actually the reverse of a reaction that we studied in Chapter 11. In Chapter 11, we introduced a hydration reaction. Now we're doing a dehydration reaction. So what we did in Chapter 11 was effectively looking at the reverse reaction, where we had an alkene, we treated it with a strong acid. The example that we used in Chapter 11 was sulfuric acid, H2SO4. And then what we could do is, remember when I said add the water across the bond? Well, that's what we did in Chapter 11. We're doing the reverse when we're dealing with an alcohol. In this case, we're actually dehydrating or removing water, which is H2O. And a couple things we need to keep in mind. So a lot of times in the past, what we've done is we've kind of we draw structures or we write down chemical formula, but we're not really tracking where the atoms are going. In organic chemistry, and from now on, we're really going to have to pay attention to exactly what atoms are reacting and which ones are being taken off or removed to a particular molecule. So we are going to lose an H and we are going to lose an OH, but they need to be from adjacent carbon atoms. The reason for that is because chemistry is not magic and things need to take place in space together. And so these atoms here, the OH and the H, form water. Well, what I had to do was break that bond and this bond. And the way that I keep carbon having, basically I have to make sure my electrons, basically I can't add electrons, I can't take away electrons. I need to use all the parts that are given to me. So we could spend a lot of time tracking where the electrons go, or we can do that. We can do that if you guys want to. But right now we're going to take the bird's eye view. I pulled off that water. It ended up here. And then to make sure carbon has 4 bonds, some of those electrons were used to form this new double bond. So Long story short, you have an alcohol, you treat it with acid and heat. If there's an H and an OH that are adjacent to each other, they can be removed as water, and then you form an alkene. So what else can we do with alcohol reactions? So we can deal with oxidation reduction, and that's what I was kind of insinuating in the very first slide, right? So for us, we said we're taking a little less detailed approach, but a more useful approach for organic chemistry of defining oxidation and reduction. So we said oxidation is going to increase the number of carbon-oxygen bonds. So just like I said in the first slide, adding oxygen. We're not necessarily adding more oxygen, but we're connecting more bonds. So that's going to fall into our definition of oxidation. It's also losing hydrogen atoms, which is going to be the opposite of reduction, which is oxidation. Reduction, right, we said is going to reduce the number of bonds between carbon and oxygen atoms. We also defined it as you could be adding H. It's not always the case, but it's one of the older definitions that will help us track things, what's happening in organic reactions. So we can start with something simple as ethane. So we don't know this reaction and we're not going to cover it. We can oxidize ethane. It requires very reactive reactants. So in a way, it literally is going to rip an H off. You need a very strong oxidant to oxidize an alkane. And I just lost my connection to my iPad. All right, I think it's back. All right, so we're not going to worry too much about that. But we can use it as a starting point because here's our primary alcohol. So now we went from ethane to ethanol. And it was oxidized. Why? Because I added an H. There we go. So one round of oxidation turned an alkane into a primary alcohol. I could also reduce it again, right? It's possible to do that. Reduction means I'm going to either reduce the number of carbon-oxygen bonds or add H's. That's exactly what's happening. Or I could go forward and oxidize it again. Again, we're not specifying our oxidizing agents. They're usually pretty strong to do these, but this reaction is pretty straightforward in terms of, like, you could pull this off the shelf and do it really quick. We can take a primary alcohol like ethanol. If we oxidize it one more, so we're going to increase the number of bonds to oxygen, and this is going to turn it to ethanal. Right? Again, we can keep track of what's happening. I've increased the number of bonds to oxygen. That's oxidation. I've also pulled off one of the H's. It's not shown in the chemical reaction. It's just going away. Usually it gets pulled off by whatever the oxidizing agent is and just floats away with that. So we're not tracking that, but we can see an H was removed because there it was and there it's not. So we did oxidize it, and we can oxidize it one further. So we can now go from ethanal, and we'll deal with this in subsequent chapters, but this will now become ethanoic acid, which is a carboxylic acid. So we're basically stuck there. You can't oxidize any more from there. So we've gone from ethane all the way up to ethanoic acid by oxidizing. And you can do everything in the reverse as well. It's just keeping track of, am I adding H bonds to oxygen and carbon? Am I adding H's, subtracting H's? It's basically giving you 4 different ways to answer the same question. So keeping track of your oxygens and hydrogens. So we'll just do it a little bit slower in between for each individual reaction. So I have a primary alcohol. Again, remind ourselves what primary means. That carbonyl carbon's attached to 2 hydrogens and only 1 carbon. So 1 carbon makes it primary. If I oxidize this, that H is going to be removed and a new bond is created between the carbonyl oxygen and the oxygen. So the carbon and the oxygen, we go from primary alcohol to aldehyde. And again, you don't need to memorize all of this as long as you get comfortable with looking at the structure and then saying, oh, am I oxidizing or reducing, and then being comfortable changing the structure. So it's going to come down to practice. You can start with memorization, but I really do suggest practice on this because organic chemistry can not blow out of control, but it adds on itself very quickly. So getting more comfortable with any situation rather than memorizing is going to probably be in your best bet. And again, what we could do is take our, say, an aldehyde. Oh, so first order, so remember, sorry, this is whatever I kind of said. But we've gone from alcohol to aldehyde. I can go from aldehyde, oxidize it again to carboxylic acid, which again, we haven't seen yet, but if we do track what's happening, well, I can't increase any more carbon-oxygen bonds with that carbonyl oxygen, but I could put on more more O's that way by attaching another oxygen. Why do I have to stop at carboxylic acid? Why can't I oxidize it anymore? Because if I did something like this, there's my methyl group, there's my original carbonyl carbon. If I somehow oxidize that more, what I have now is 5 bonds to carbon, and we know that can't happen. So this kind of ends our oxidation of basically alkanes to alcohols to aldehydes to carboxylic acid. So I'm not going to keep going through as detailed that I did before because I think we're starting to catch on to things. But again, you don't just have to start with a primary alcohol. What if I start with a tertiary alcohol? So what I mean by tertiary, 1, 2 carbons are attached to that carbonyl oxygen in red. So what could I do? If I'm going to oxidize it, remove an H, create a bond with that new carbonyl carbon and oxygen. That's what I see in my second structure here, and it turned it into a ketone. Again, that's actually the end of the line. I can't oxidize that any further, because if I tried to even put an alcohol group on, again, I'm at 5 bonds to carbon, and that's not going to fly. The last thing we'll look at is going to be tertiary alcohols, and this is the easiest one. There's no reaction, because I got my tertiary alcohol says my carbonyl carbons attached to 3 other carbons. It's already attached to one, the alcohol group. So if I did try to oxidize it, again, I'm at 5 bonds with carbon, and that's not going to fly. So tertiary alcohols do not react. So summary, primary alcohols go to aldehydes, which could ultimately go to carboxylic acid. Right? We haven't got there yet, so don't worry. So as far as you're concerned, that's where we're going. I could go with secondary alcohols. Those form ketones when oxidized. And then tertiary alcohols, when oxidized, sorry for that, no reaction. Oxidation of thiols. Oops, did I skip ahead too much? I did. Sorry, there's a little bit of a lag. So oxidation of thiols are a little bit different. Rather than forming additional double bonds, what ends up happening with thiols, even though they're right below oxygen on the periodic table, I foreshadowed this in the earlier lectures that sulfur and oxygen, the thiols and the alcohols, have distinctly different reactivities. What ends up happening with thiols, I'm sorry for so many text messages, I'll stop that, is if you get 2 thiols in proximity to each other, what will end up happening is those 2 H's that are there will be removed, sometimes as hydrogen gas, not always, and then a new bond between the sulfur will form. This new bond, a sulfide bond, sulfur is making the bond. There's, one of my important that's reactions that happen, but this is the biochemistry. Why you see here it's saying I have some kind of protein chain, maybe it's the same protein, but whatever it is, which means at the end. And so I don't think I specifically meant symbol right there means oxidation. Sometimes, but build oxidation there. A sulfide group between the two. If you've ever had your hair, exactly what's happening. Really formed because there's a lot of sulfur. Cysteine contains the thiol group. In human hair, cysteine you tend to form the, and so you can either break those bonds, then forms in your hair. So what we did in the first part, remember, we built up from primary and secondary alcohols up into aldehydes and ketones respectively. That just means we can do the reverse reaction, right? We already said we can take primary alcohols and then oxidize them to form aldehydes. So if I do the reverse reaction, it's reduction. Well, there's my H. I'm using a platinum catalyst again to make the reaction go a little bit quicker, but I'm effectively reducing the number of bonds. That's where the word reduction comes from. Reducing the number of bonds between the carbonyl, carbon, and oxygen. How do I reduce it? By adding hydrogen. And so I can see that it turns back into my primary alcohol, and then I got to make sure that all of my carbon has 4 bonds. So where that other H went, one H from the hydrogen went to the carbonyl oxygen, the other H goes to the carbonyl. And then I can do, then doesn't have to be or palladium. It's not as good of a catalyst, but we could take something like the common name, that carbonyl, other H goes to carbon. That's, we've gone from a secondary ketone, secondary alcohol. That we had on the pre-alcohol, this is we've our ketone, so reverse reaction when we reduce it. So it seems like you're learning a lot of reactions, but you're not. You just learned a forward and a reverse. That's it. Oxidation and reduction. So that's why alcohols and ketones are being introduced at the same time, is because one simple step can convert one to the other. So this is the only practice problem I have for this brief lecture. I'll do more later. I think a lot of it's just going to come down to just practice to get this stuff. I don't think rote memorization is going to work very well. At least that's my interpretation. All right, so we're given this molecule here. I can see right off the bat, I have a chain of carbons, and then my predominantly, or at least my more important functional group is going to be my alcohol group. So I'm oxidizing an alcohol. That means my only choices are aldehyde, ketone, and no reaction, which is actually a lot of choices. But if I remember, aldehydes come from primary alcohols. Ketones come from second reaction, occurs from. So I already know cross some things out. I can cross out, because I know I'm starting with an alcohol, somehow I'm trying to form. We don't know that reaction, but actually, no, so sorry about the reaction, but we know it, but we're looking at that one right off the list is to ask the question, what degree compound that I have, is it primary or secondary? And then there are connected to that, and then 2, remember, they're at least carbon based, so we don't care about H's. So that's telling me it's ketone, so then I have my ketone. Can't possibly be right. Here D is that's effectively saying no, so it's not a tertiary. And look, how do I know it's a ketone? Functional group is connected to 2 carbons. And that's exactly what we have here. So that's going to end chapter 12. I know that went a little bit quick, but I think most of it's going to come down to is watching the theory, and a lot of it's going to come down to practice. So it's very different than the general chemistry component, where a lot of it could be like, okay, I read it, I memorize it, I say it. Organic chemistry is like, here's an idea, now apply it to a whole set of molecules. And that's going to be the new challenge coming into this section of the course.